Welcome back to multivariate calculus. In this video, we're going to be looking at the cylindrical coordinate system. In addition to that, we're going to be investigating a little bit more carefully what we mean by a cylinder and some of the tools that we can use based on cylindrical coordinates. So let's start there. In geometry in middle school and high school, you certainly were introduced to an idea known as the right circular cylinder. The right circular cylinder is this object which has a circle on the top, straight sides, and a circle on the bottom. One of the key features of the right circular cylinder is that it forms right angles, right? The surface that is the bottom and the surface that is the side are a right angle of each other. A cylinder doesn't have to be a right cylinder. You can have a cylinder that goes off in a slanty shape. Get my head out of the way so you can actually see that drawing. It's still a circular cylinder because the top and bottom are still circles, but it is no longer right. Well, even that's not strictly necessary. We can make the top of the cylinder any shape we want, as long as the bottom is the exact same shape. And that's very difficult for me to do, so forgive the fact that those don't really look the same, but let's pretend the top and bottom are the same shape. For the sake of easing our calculations, I am going to look at cylinders where we are looking at right cylinders. If you want a cylinder that is not right, what we're going to want to do is take a cylinder that is right and simply cut it at some arbitrary angle. And then that will approximate a cylinder that is not right. But setting up right cylinders is going to make our lives easier. Just like when you learned in graphing lines in 2 dimensions, if you have an equation that is missing a variable, it will give you a horizontal line or a vertical line. In this case, the vertical line is given by x equals k. Same if you have an equation in 3 variables that's missing a variable, and traditionally we will be missing the z, you're going to end up with a surface that goes straight up and down. So here I have the equation of a circle. Specifically, I graphed the circle with a radius of 3. If I tilt my axes and get the xy plane that we're accustomed to seeing, okay, the surface is so thin you can't see anything, but if I tilt just a little bit, you can get the sense of the perfect circle that we are looking down on. And we're just taking that perfect circle and building walls straight up in order to get this 3-dimensional right circular cylinder. I can do that with any sort of an equation. It doesn't matter what the equation looks like. It doesn't even matter if it actually connects at the ends, although GeoGebra can be a little bit finicky sometimes with setting that up. So for example, if I look at the equation, y equals x cubed minus 3x, I know that I can graph this in 2 dimensions. Let's see, x is equal to, or y is equal to 0 when x is 0, or the square root of 3, or the negative of the square root of 3. Because it's positive, it's going to be going up that way, so it's got to be going something like that is this graph. And then I just want you to visualize extending that out into 3 dimensions. Again, if I go into GeoGebra, I can graph this thing, although the equation for doing so is not very straightforward. We'll be talking about parametric surfaces much later in the course, and it turns out that to graph something like this in GeoGebra, you need a parametric surface. But if I try to look at it top down, you can see that in the XY plane, we've got a curve that looks exactly like the graph of y equals x cubed minus 3x, a nice cubic graph. And if I tilt off to the side, you can see that I've got some straight walls going on. And it does continue indefinitely, but it's cut off here because there's only so much space that we are able to graph, and for the sake of not using too much memory. But this shape, weird as it may seem, is still a cylinder. And so we can do things with cylinders that seem a little bit arbitrary. I guess it makes sense to focus mostly on the right circular cylinder because that does give us a couple of other ideas. When you're talking about a right circular cylinder, you're talking about a circle. And when you're talking about a circle in two-dimensional space, very soon you start talking about polar coordinates. But what if we took the exact same rules that we've just been talking about with cylinders and let them work for polar coordinates as well? We can take our polar coordinates and just lift them up or push them down to get various different z values. So instead of having just an r and a theta for polar coordinates, what if we also include a value for z? With that, you can find any point on a cylinder, on a right circular cylinder, and that's why we call these the cylindrical coordinates, or if you want to be fancy, the cylindrical polar coordinates. And we can take something that's given to us in rectangular coordinates, describe it in cylindrical coordinates. We can take something that's given to us in cylindrical coordinates and describe it in rectangular coordinates the same way you do conversions between rectangular and polar coordinates. It's literally the same equations, right? We add in that z is equal to z because that doesn't change at all. And we have all of the conversions that we need for cylindrical coordinates. Rather than spending too much time thinking about that aspect of things, one of my favorite applications of cylindrical coordinates is working with surfaces of revolution. Surfaces of revolution are an idea that was introduced to you in calculus of a single variable. We generally looked at things on a horizontal axis where we had some curve y equals f of x, and we revolved it around the x-axis to get this three-dimensional thing. I describe it as a wood-turning project. If you think about our three-dimensional space, we can find a new way of describing this same behavior, although it's going to be a little bit messy. Once you see how it works, it's going to become very obvious, and you're going to start to wonder, why do we include surfaces of revolution in Calc 2 when we can do them here and it's so much easier? All right, but let's set up our normal coordinate axes. Let's look at our point Let's remember that we can take this point and just drop it down somewhere into space. And that gives us the picture of what this thing looks like. The angle theta is measured from the positive x-axis in the direction of the positive y-axis, following the right-hand rule. Nothing has changed there. And then r is measured out from the origin in the xy plane directly to the shadow of the point in question. And so what we want to do here that's going to be a little bit different, if we pick a specific value of theta, we can look at the two-dimensional surface formed by the r and z axis for, again, some arbitrary fixed value of theta. And here's where things get interesting. In a surface of revolution, we revolved around the horizontal axis, but we could have just as easily revolved around the vertical axis. We can set up our shape here. We can set up that z is some function of r. And we can create our surface of revolution like that. It absolutely works. It gives us the same kind of a curve that we saw before. And the way that we do that is, instead of saying that this is a specific fixed value of theta, we simply claim that all values of theta have the same trace. Once we've done that, we can set this up. We can graph our curve just like that. This is almost certainly the most useful situation of cylindrical coordinates. Cylindrical coordinates become the most powerful when your value of theta is irrelevant to the discussion. Right. So if we have an equation that we want to try to graph, right? So z equals some function of r. So maybe z is equal to r to the 2/3 power. That's something that we can graph. It has a kind of interesting looking graph in its own right. In order to use computer software to graph this, we need to replace z with y. We need to replace r with x. That sets up our axes to look the way we expect. But that gives us this nice curve that we can study. So we have that z equals r to the 2/3 power gives us a graph that's going to look something like this. And because we're thinking about r in polar coordinates, we only want positive values of r. And so we can graph kind of what's going on here. And maybe we'll just look at the part of it that goes between 0, 0 and 1, 1. If we want this to be a surface of revolution, we can convert from cylindrical coordinates into rectangular coordinates using the equation, the rule that r squared equals x squared plus y squared. Now, r to the 2/3 power, remember, is the same thing as r squared to the 1/3 power. And so we can substitute in and write this as z equals x squared plus y squared to the 1/3 power. Let's go over to GeoGebra and let's graph exactly that. Z equals x squared plus y squared, the whole thing raised to the 1/3 power. If I manipulate this so that I'm looking at, well, anything where the xy plane is flat, you can see that I've got the exact same graph that I had for z equals r to the 2/3 in 2 dimensions. But looking at it in 3 dimensions, you can kind of see how the curve is going to go. You can look down on it, and it's very difficult to see the circles there. Looking up on it, again, kind of difficult. But if you look at it at different angles, you can start to see that this is just a bunch of circles um, that are rapidly spreading apart. All right. So there is one application of cylindrical coordinates. Before I wrap up here, one other thing that I really like to focus on are the constant surfaces. In rectangular coordinates, the constant surfaces, x equals c, y equals c, or z equals c, are planes at right angles to the corresponding axis. X equals c is a plane that is perpendicular to the x-axis. Y equals c is a plane perpendicular to the y-axis. Z equals c is a plane perpendicular to the z-axis. In cylindrical coordinates, well, we've got r equals c, we've got theta equals c, and we've got z equals c. Z equals c we just talked about. The parameter z is the same in polar and rectangular coordinates. Right? In 2 dimensions, r equals c is a circle of radius c. So in 3 dimensions, it's going to give us the right circular cylinder of radius 3. In 2 dimensions, theta equals c gives us a half a line. Right? It's a line that points from the origin out in one direction. It's a ray. In 3 dimensions, this one is the hardest thing to visualize of everything. But in 3 dimensions, we're going to have that line, and it's going to extend up and give us a plane. But again, only half of a plane. It's going to be the part of the plane that starts at the z-axis and extends outward in whichever direction we've claimed that we want. All right, so this gives us a half plane which ends on the z-axis. That's not all that useful, although it could be. The right circular cylinder a little bit more useful and gives us something we can work with. All right, but to wrap up, let's look at something that you can try. As I said, I think the most interesting application of cylindrical coordinates is looking at surfaces of revolution. So I would like to revolve the equation z equals r squared minus the square root of r about the z-axis. I want to write the equation for the surface, write the equation in rectangular coordinates, and then graph it to see what we end up with. All right, so take a few minutes, see where you can get to with that one, and I'll see you in the next video.